Welcome to day 18 of the Advent of Code. Today is all about lexing, parsing, and evaluating formulas inside strings. For example, here we have a formula consisting of numbers, plus signs, and stars. And here's a more complicated formula that also has nested sub-expressions inside parentheses. Okay, and before we dive straight into the implementation, let's look at the grammar for the first part. So expressions are made up of one primary, for example, a number, and then an arbitrary repetition of operator followed by another primary. Okay, and what's a primary? A primary can be a number, like 1, 2, 3, 4, 5, 6, but it can also be another expression wrapped inside parents, right? For example, this guy. Okay, and you already see the recursion here, probably. So expression is defined in terms of primary, and primary is defined in terms of expression. But of course, the recursion bottoms out as soon as we pick the left side here. Okay, but in theory, you could nest these parentheses arbitrarily deep. Okay, and then we're given a choice between functional parsing and imperative parsing. So I'm going to use a recursive descent parser, which means that for every rule, I'm going to write a function that is named just like the left-hand side here, and the right-hand side will guide us through the implementation. So what would be the type signatures if we were to write them down? So in a functional parser, we pass in the lexemes, which is just a sequence of substrings that are interesting to us. And then we would get back a result. Let's say the primary parse function would look at the complete sequence. It would turn the 1 into an integer, and then it would return the non-consumed rest of the sequence back to the caller. That would be this guy. Okay, whereas in an imperative parse, we have some mutable state in the background that remembers where inside the sequence we currently are. So we don't have to pass it in and we don't have to pass it out. We just pass the result back. Okay, so that makes the implementation, I would say, simpler for people who are more used to imperative programming. And let's do it this way. I think this is interesting to see how to use mutable state in Clojure. Okay, so here you see how I lex the input strings, how I turn it into a sequence of lexemes. That's just good old regular expressions. Okay, but this is just a normal let binding to a sequence. We can't mutate the lexemes binding. And in order to have the possibility of mutation, I can wrap that in a volatile. That would be the simplest approach. So volatile is one of a handful of so-called identities in Clojure. Identities give you, it's basically a wrapper around a value, and you can point to different values in different points in time. And this is just the simplest one. Okay, and then we could start, defining functions. So we would define expression as a function, taking no arguments, and somehow it will call primary. And maybe let's do it. Somehow it will call primary, and then primary would also be a function that's somehow called expression. Of course, now we get an error because the Clojure compiler reads the code from top to bottom, and at this point primary isn't defined yet. We could forward declare it, but there's an even better approach. Let me show you. We can use let fun, which lets us define an arbitrary amount of functions which all can call each other. That's quite nice. Okay, so we want an expression function that takes no arguments and does something, and then later we also want a primary function that takes no arguments and does something. Okay, but let's define some helper functions first. So I like to have a function called current, right? That simply looks at the lexemes. So this would be the volatile. If we want to have the value inside the volatile, we have to dereference it. And that would be the entire sequence. So I just want the first lexeme of those, okay? Okay. Right, and then let's have another function. I call that accept. What does accept do? It yeah, basically resets the lexemes value to the rest of the lexemes, and we can do that quite succinctly with the vswap function and simply pass in the volatile and the function that we want to apply to the value inside the volatile, and that then becomes the new value. Okay, does everything compile for now? Yes. Okay, cool. So what does expression have to do? I would say we start with the loop. The loop basically is an implementation of this optional repetition here. But of course, we must start with the primary. So let's say temp should be the result of calling primary. And then we have to see whether or not we have an operator here. So we can simply case over the current, and we have to do something if it's a times. Let's see, we have to do multiple things. That's why I use a do. We have to accept the multiplication sign, and then we need to recur and say we want to multiply the result so far with the result of calling primary again. Okay, cool. So basically we map the multiplication sign of our toy language to the multiplication of Clojure, and that happens to be the same character, but that's just a coincidence. It doesn't have to be that way. Okay, so that would be that case. Yeah, then let's maybe simply do copy paste. So what do we have to do for plus? Except exactly the same thing, except we have to add the both results. Okay, and if it's neither times nor plus, then either we are at the end of the sequence or we are inside a sub-expression and we have reached the closing paren. So we can simply return the result so far. We can't do anything else for now in this activation of the expression function. Okay, cool. Does it compile? Yes. Good. So then what do we have to do inside the primary? Also, let's look at the current lexeme. If it's an opening paren, what do we have to do? We want to accept the opening paren, and then we have to pass the parenthesized expression, right? So let's call expression. Here's the mutual recursion. And then when will the expression function return? When it hits the closing paren. So we just accept it and silently assume that, assume closing paren here. Okay, so we don't treat errors in our input very well, but that's okay. Okay, and then we have to return the temp, of course. Okay, right, and if it isn't an opening paren, then it's probably an integer as a string, so we have to parse it. Parse int of the current. Okay, and then we accept the current string, and then we return the temp. Okay, does that compile? Yeah, compiles. And then how do we start our little machine? We simply call the expression function, because that's where everything starts, right? Then we can get rid of this nonsense here. Okay, still compiles. So let's see if we now run this, what happens. We get 71 and 51, and that's exactly what we expected. That's good. Okay, so maybe now we can also look at the large input. So in case you don't know, this is special reader syntax that says please ignore the next form. So let's remove that, and let's remove that. And then we get this very large result for part 1, and that's correct. Okay, cool. So maybe let's copy that for part 2. Here's part 2. The only difference in part 2 is that now the multiplication and the addition have different precedences. Before they had the same precedence, which was rather unusual. But here the precedences are also unusual. So normally you would expect the plus at the top level and the multiplication below. But here it's exactly the other way around, probably to prevent you from simply calling a built-in Python function or JavaScript function to evaluate your string. Okay, so instead of one function called expression, now we have two functions, product and sum, where product is defined in terms of sum and sum is defined in terms of primary. Okay, so this should be doable with a little bit of copy-paste. So this would be the product, And the product is used in the mutual recursion down here and in the starting of the machine. Okay, and then we only want the times there, right? So let's get rid of this. And we want to call the sum function instead of the primary. Okay, the sum function only wants to add, but it calls primary. That is correct. Here, let me look over this one more time. Product sum, 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 primary, 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 product. Yeah, that's looking good to me. Okay, let's see. We have 231 and 51, and that's exactly the result that we expected. Yeah. Okay, cool. So from a Clojure perspective, we only learned two things, but I think they're quite interesting. So we have the volatile, which is a one of Clojure's identities, a mutable wrapper around a value, and you can update that with the vswap function. And you have similar functions for other identities in Clojure, like atoms and refs. Okay, we get some, thread safety guarantees. So volatile means different threads will see each other's writes to the variable. We don't really need that because evaluate is only ever executed by one thread with the same volatile. But this is just the simplest way to get an identity in Clojure. I think if you know of a simpler way than volatile, then let me know. Okay, cool. And then we saw the deref function to get at the value inside the volatile, and you can abbreviate this with an @ sign. That also works. Okay, and then we saw the let fun that lets us define multiple functions that can reference each other as explained in the comment here. Okay, cool. So that was basically the Clojure part, and the the parsing. In reality, maybe at a certain level of complexity, you would use a parsing library like instaparse or Antler or some parser combinator thing in Haskell. But for such a simple puzzle, I thought let's do it by hand. Okay, so basically you start with a grammar. The precedences of your operators are reflected in the grammar. The strongest binding operators are below, and the least strongly binding are at the top. And then you simply implement functions for your rules, where the implementation of the function is guided by the right-hand side. Okay, cool. And in our case, we said these repetitions we implement with loops, and these alternatives we implement with cases. Okay, cool. Yeah, and what is rather unusual is seeing these functions without arguments. So this is a strong hint that this function has a side effect. So we don't pass anything to it, but it returns or it does something interesting, even though we don't pass anything into it, and we completely ignore the result. So it must have some effect, otherwise it wouldn't make sense to call it. Okay, so maybe it would be a good idea to put exclamation marks at the end of those functions. Okay, cool. Yeah, I think this is a really interesting exercise. Can I show you the entire thing on one screen? No, it's too big for that. Maybe the first one. It almost fits. I think this is an interesting exercise, and of course there's lots of possible ways to implement this. So recursive descent is a natural choice if you've done it before. So I guess most of you will have used recursive descent. If you have used recursive descent, let me know if you implemented it in a functional fashion or in an imperative fashion, or if you used a different approach like the shunting yard algorithm or a library or some other ad hoc approach. Let me know in the comment section below.